Chapter 2.5, Postulates and Intuitive Proof. A postulate is a statement which is taken to be true without proof. When we develop a field of mathematics like geometry, there are certain basic statements that we take to be true. We don't actually prove that they're true because there's not really a way to prove that they're true, but we know that they are. We internally know that they're true, and then we build the study of that field of mathematics, for example, geometry, upon those basic truths. The ones that we have that we build geometry upon, we study those in Chapter 1. And I don't want you to memorize them word by word, but be able to paraphrase them. For example, the first one is through any 2 points, there is exactly one line. You can paraphrase it as 2 points, give us one line. We also have through any 3 non-collinear points, there's exactly one plane. Non-collinear means they're not all on the same line. A line contains at least 2 points. We know a line contains an infinite number of points, but we only need 2 points to name the line. A plane contains at least 3 non-collinear points. Again, a plane goes infinitely in all directions and contains an infinite number of points, but we only need 3 non-collinear points to define the plane. If 2 points lie in a plane, then the entire line containing those points lie in the plane. We can paraphrase that when we're giving an example or justifying a step that we take in a proof by saying if a line lies in a plane, then the entire line lies in the plane. If 2 lines intersect, then they intersect in a point. If 2 planes intersect, then their intersection is a line. You can think of that intersection, for example, as a wall and a ceiling. Those intersect in a line. We studied inductive reasoning in Chapter 2.1. Inductive reasoning uses patterns or examples. Examples, observations. To make a conjecture or to make a conclusion. Conjecture is drawing a conclusion. So for example, if we look at the pattern of 2, 4, 6, 8, we would make a conjecture that the next term is 10 by looking at the pattern. Deductive reasoning, which is what we're going to get into for chapters 2.5 through 2.8, uses facts, rules, definitions, properties to reach a logical conclusion. So deductive reasoning uses facts, properties, definitions, to reach a logical conclusion. So for A and B, we want to state, is it deductive or inductive reasoning? The first one is every time Katie has worn her favorite socks to a softball game, she has gotten at least one hit. Katie is wearing her favorite socks to a game tonight, so she concludes that she will get at least one hit tonight. So there's no rule that's saying that she's going to get a hit. It is inductive reasoning. The next one, if John is late making his car insurance payment, he will be assessed a late fee of $50. John's payment is late this month, so he concludes that he will be assessed a late fee of $50. This is deductive because there is a rule in his contract that says he'll be assessed a late fee. In the next problems, we're going to determine if the statement is always, sometimes, or never true. If plane T contains line EF and line EF contains point G, then plane T contains point G. So we have a plane, which we're going to name T. It contains line EF, and they're telling us that G is somewhere on that line. And so it's always true and the reason that's so is that if 2 points lie in a plane, then the entire line does. Problem B says line GH contains 3 non-collinear points. Well, the definition of non-collinear is not on the same line. So GH is a line, it can't contain non-collinear points, so this is never true. Problem C says plane A and plane B plane A and plane B intersect in exactly 1 point. Planes intersect in a line, so this could be never true because planes intersect in a line. Problem D, point N lies in plane X and point R lies in plane Z. You can draw only one line that contains both points N and R. And this is always true because through 2 points is one line, or exactly one line. When we do proofs, we're going to do only 2-column proofs in this class. We're not going to do paragraph proofs. We're not going to do flowcharts. We'll just do 2-column proofs that give the statements and the reasons. When you create a 2-column proof, I don't care if you put statement and reasons at the top of the columns. It will follow the same format every time. We always start with our given. M is the midpoint of XY, and that is given. We then decide what we know for sure about M being the midpoint, and looking at what we have to prove. We want to prove that XM is congruent to MY, so we ask ourselves, if M is the midpoint of XY, what do we know about XM and MY? Well, we know that their measurements are equal to each other. And that's by the definition of midpoint. We need to prove that those segments are congruent to each other. So XM is congruent to MY, and that's by the definition of congruence. Now, on an assessment in this class, or whether it's a quiz or a group assessment or an assessment that I'm actually asking you to complete on your own, the proofs will either be really, really short like this, or the majority of them are going to be fill in the blank. But we're going to go through quite a few proofs in the class and learn how to walk our way through the proofs and how we think about it so that you can understand how to do the fill in the blanks. Because when you do that, you're going to have to read about what happened before the blank and what reads after the blank to know how to fill in that blank. But in this proof right here, we use the definition of midpoint, and the definition of midpoint is if M is the midpoint of segment AB, then AM equals MB. So we have this picture here, A and B, midpoint M, and that is equal to that. The midpoint theorem is if M is the midpoint of AB, then segment AM is congruent to segment MB. And in our book, that is the definition of midpoint, and that is the midpoint theorem. Okay, so we're going to move on to the next proof. And the next proof gives us that M is the midpoint of BC. So looking at a picture, we have BC and we have M. We know that is equal to that. So starting with the given, now we know that since M is the midpoint of BC, we know that BM equals MC, and that's by the definition of midpoint. And we need to take away these segment signs over the top of those. Okay, so we know that BM is equal to MC, so we have brought the BM into our argument here, but we still need to bring BC into our argument. We need to introduce that into the courtroom. So the next step would be that BM plus MC equals BC. And now we've introduced BC into the argument, and that's by segment addition. And we learned that in chapter 1. Now in my argument, or what I want to prove, only includes BM and BC, so I can replace this MC here with the BM. So I'm going to substitute that in. So BM plus BM equals BC, and that was substitution. And we took information from 2 and substituted into step 3. We know that BM plus BM is 2BM, so 2BM equals BC. Again, that would be substitution. The next step, we would multiply by 1/2 or divide by 2. So now I know that BM equals 1/2 BC. And do the division property. Our book calls this midpoint theorem number 2. So we're going to move on to the next proof, and in this proof we'll start with the given. BC is congruent to EF. M is the midpoint of BC. N is the midpoint of EF. And that was our given. So we know that M is the midpoint of BC. We know these are equal to each other, and we know that this is equal because N's the midpoint of that. But using midpoint theorem number 2, we know that BM, which is one of the things we're looking for in our proof, is equal to 1/2 BC. And we know that EN, which is the other portion of what we want to prove, is equal to 1/2 EF. And that was from midpoint theorem 2. We were also given that BC is congruent to EF, which means that BC equals EF. And that's by definition of congruence. We can multiply both sides by 1/2. And that's the multiplication property. Well, 1/2 BC is equal to BM, and 1/2 EF is equal to EN. So we can substitute those into this, and we will have that 1/2 BC equals BM, and 1/2 EF equals EN. And that's by substitution. We took information from 2 and substituted it into 4. We were asked to prove that they were congruent, so we need one more step. So BM is congruent to EN, and that's the definition of congruence. So to begin this proof, we list our given. S is the midpoint of QP. P is the midpoint of ST. And T is the midpoint of PR. Now, since S is the midpoint of QP, then we know that QS is equal to SP. And since P is the midpoint of ST, we know that SP is equal to PT. So looking at the picture again, we have QP, and S is the midpoint, so we know that's congruent to that. Then we also have the SP right here, and we know then that SP is congruent to ST. And this is by definition of midpoint. Now we have QS equals SP, but then SP equals PT. And some of you might remember the transitive property from Algebra 1. And the transitive property in Algebra 1 says that if A equals B and B equals C, then A equals C, and that's called the transitive property. So we have that pattern here. QS equals SP and SP equals PT. So then QS equals PT, and that is the transitive property. Basically, it's like the substitution too. I would substitute QS in for SP. We haven't used the fact that T is the midpoint of PR yet. So since T is the midpoint, we know that PT equals TR. Definition of midpoint. And again, we have QS equals PT, but PT also equals TR. So QS equals TR, and that's by the transitive property. We were asked to prove that they're congruent, so we need one last step. QS is congruent to TR, and that's by definition a congruence. We have two remaining proofs, and they're fairly short proofs. In this one, we're given that BD is the angle bisector. And that was given. If BD bisects this angle ABD, then we know it cuts into two equal angles. So since BD is an angle bisector, we know the measure of angle ABD has to equal the measure of angle CBD. And that's definition of angle bisector. We needed to prove that they're congruent, so we have to take the one final step. Angle ABD is congruent to angle CBD, and that's by definition of congruence. The last proof, we have that angle A is congruent to angle D, and that angle D is congruent to angle E. And that was our given. Changing this to measurements, we have that measure of angle A is equal to the measure of angle D, and then the measure of angle D equals the measure of angle E, and that's by definition a congruence. We have measure of angle A is equal to measure of angle D, and that measure of angle D is equal to the measure of angle E. So we have the measure of angle A is equal to the measure of angle E by transitive property. And we wanted to prove congruence, so we have one final step. Angle A is congruent to angle E, and that's by definition a congruence. And that concludes the lesson for 2.5.